This work presents a method for localizing primitive shapes in a dense point cloud computed by the RGB-D SLAM system. The primitive shapes are incrementally modeled by fusing the shapes estimated at previous frames in the SLAM. This process stably generates a shape map containing only primitives. Specifically, the history of the fusing process is used to avoid the influence of error accumulation in the SLAM. We used real-time appearance-based mapping as our visual SLAM system. It includes all basic functions for RGB-D SLAM such as frame-to-frame and frame-to-map registration with ICP and visual features. The system outputs the point cloud in the global coordinate system. At this point, we extract primitive shapes from a point cloud using a technique called efficient ransack. However, due to noise or partial views of the objects, this method frequently outputs inaccurate results, such as a plane being a part of a large cylinder. To prevent this, we added a credibility condition for spheres and cylinders that relates the number of points associated with a shape and its radius. In other words, a point cloud must be the representative part of a shape, such that a large shape needs many points. To match a primitive extracted in the latest frame with the one in the shape map, we use the primitive parameters, such as normal and radius. The same type of shapes with similar parameters are matched. For instance, these two spheres are matched only if the ratio of their radii is within a certain range, their distance is less than a certain value, and these matching conditions are subjects to defined parameters. Here, we determine the most probable parameters for the primitives based on the entire history of extraction. We use a weighting scheme that corresponds to the number of times it has been updated. This gives an equal importance to the shape in the past frames that have been used for the update since the beginning. Finally, the point cloud of the final shape, in red, is updated by projecting the points of the detected sphere, in blue, and the one in the map, in green. As the capture continues, the point cloud of each shape is downsampled to avoid unnecessary accumulation of points. Our evaluation showed that the error on measuring the radius of spheres and cylinders varies between 0.1 and 4.6 mm, and that it is difficult to model spheres that have the radius smaller than 30.0 mm. The execution time is proportional to the number of points. However, the modeling process was executed in less than 100 milliseconds on average in a standard desktop.